Hey, Dr. John, how are you? How you doing, Dr. Tran?
Hey Steven, how's it going?
Oh, I can't complain. I mean, I could, but I'm not going to. We're talking about element types, more element types this week.
Yep. Yeah, so we're going to be talking about shell and beam elements. So they're special element types.
Hi, Professor.
Oh, hi.
I saw you on YouTube.
Oh, cool. Yeah, I'm on YouTube. Which videos did you see?
The fluids one.
Oh, okay. Great.
Yeah, I'm the
Great.
one who asked about them, the one that emailed
Oh, okay. Okay, cool.
you.
Are you taking fluids this semester?
Yeah,
Okay. Who are you taking it with?
Darren Banks.
Okay. Yeah, he's really great. He's a good college of mine. Is that a virtual class or is it a hybrid class?
It's virtual.
Okay. Oh, completely virtual.
Yeah.
Okay. Yeah, makes sense. Probably he has good reasons to not want to come to campus.
Uh, working on.
How's it going, Dr. Tran?
Good. Yeah, tired, but it's just you guys know, it's just like that until the end of the semester. Constant feeling of
Yeah.
just feeling tired. I went to a concert on Friday, actually, the first time in a really long time.
Oh, that's
Um,
cool. What'd you see?
I saw Porter Robinson and Dry Wolf at LA Historical Park.
Oh,
My
wow,
fiance is a
nice.
really big fan, so I even before pandemic, I'm usually not a go to concerts kind of guy. But my girlfriend, my fiance is such a huge fan that I wanted us to go to one together. And this seemed like kind of a good chance because he's playing in LA. Both of them were playing in LA, which I guess doesn't happen that often. And so we went. Yeah, we saw. A little nervous being around that many people, but it was outside and everyone was required to be vaccinated to go inside. So I think that helped. That helped alleviate some of the concerns, but still a lot of people.
That's cool. I didn't know Porter Robinson was playing.
Yeah, I think they announced, my fiance said they announced this one kind of last minute. I think he played Friday and Saturday.
Would you say kind of like EDM music now, or?
Yeah, I mean when my fiance plays it, I enjoy it, but I usually don't, I won't listen to it on my own probably. Man, I haven't smelled that much weed in a long time though. Yeah. I feel like I woke up the next day like getting like a secondhand high just from smelling all the smoke there. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, good. Yeah, week 7 now, so yeah, we're getting up there. All right, so this week I have another ANSYS activity planned, and this will actually be the last one for a little while because after this week we're going to start to talk. We're going to go a little bit into basic finite element theory, right? So this class is kind of in a unique position because it's kind of the only finite element class that we have for undergraduates. And so I wanted to make sure that the majority of this class was based around ANSYS. But we do have to dig into the theory a little bit just because we have to kind of plan for this class as kind of like an intro where if you go off into grad school and you learn more about finite element theory either here or at another university, like you'll have that background. And so that's part of kind of the delicate juggling act of this class. And so starting next week, yeah, so we'll be going a little bit into theory. We'll do that for maybe like a few weeks, maybe three weeks, and then we're going to jump back into ANSYS stuff. Okay. But starting this week, we're going to jump into what I consider to be a little bit more advanced features in ANSYS. And so the stuff that we're going to cover this week and the ANSYS stuff that we're going to cover after all the theory stuff, maybe you're not going to use it for every single ANSYS simulation. But it is there and it can be really useful for the situation where it can be, okay, where it can work. And so this week, we're going to cover shell and beam elements. And so these are two specialized element types that work really well in the situations where they work well. And so we're going to go over what those situations are and what benefits do they give you, okay? And so we're going to go over kind of just the introduction to those to the element types today. And then on Thursday, we're going to do an activity where we actually put this in practice. And so the activity, and so for this activity, just because I know a lot of you are starting to work on the projects, I'm giving you a little bit more time for this one. And so you'll have about 2 weeks to finish this activity compared to the usual 1 week that I usually take. Okay. So I think that's it for my announcements. So are there any questions that I can answer before we get started? Okay, all right, so let's go ahead and get rolling. Okay, and so the topic for today are shell and beam elements. And my stylus is not working well. All right. And so last week, we started talking about different element types, right? And so we went over all the different shapes that you can have in 3D and in 2D, okay? And so, from here on out, I'm going to assume that we're strictly going to be working in 3D, okay? And so, you'll hear me use this term for most of the day. I'll be using the term called solid elements, right? And by solid elements, what I mean are elements that have 3 dimensions of space, right? And so in 3D, our solid element types are going to be our tetrahedrons, right? So this goes for both the linear and the quadratic versions, okay? And of course, also the hexahedrons, okay? They're called solid elements because they actually have 3 dimensions of space, okay? And so shell and beam elements, that kind of implies that these are going to be a little bit different than that, okay? And so let me start by talking about, what are the situations where you want to use solid elements, right? And so because solid elements, they're basically 3-dimensional shapes themselves. Okay. And remember when we were talking about mesh quality, we talked about, when you're using these elements, ideally you would want them to be as equilateral as possible, okay? Okay. And so what that means that all the edges and all the side and all the faces are the same, have a roughly the same size. Okay. Naturally, these are going to work well to mesh geometries that are also kind of roughly equilateral. Okay. Okay. And so what I mean by that is that if you basically take your object and you basically measure the dimensions in the x direction, you measure kind of the direction, the dimension in the y and in the z, you're going to get all roughly the same number. So it doesn't have to be exactly the same, but they should be in kind of the same ballpark. Right? I'm not sure. I think I showed some of you in this class, but if you look at the geometrical properties of your CAD model, after you open up an ANSYS, there's a property that you can look up called the bounding box, right? And all that basically means that is it takes your geometry and draws a box around it, the smallest box possible that fits in your entire geometry. Okay. And so when I say that your object is roughly equilateral each dimension, one way that you can kind of easily check that is to check the bounding box, right? And so if you check the bounding box and you check the dimensions of this box, and all of them are roughly the same magnitude, or at least the same order of magnitude, then this is probably a good, roughly speaking, it's a good object to use solid elements for. Okay. And so one object here that I think would work really well with solid elements that I can grab is this mouse, right? And so if you guys see on Zoom, right? And so you can see this mouse, if you can imagine we draw a box around it, all the dimensions are not going to be quite the same. And so the height of this mouse in this direction right here, that's obviously going to be smaller than the length and the width, right? But roughly you can say that they're about the same magnitude. So I'd say, just really roughly, I would say the height of this mouse is maybe half the length of that mouse, right? And so, we're not talking about, differences of 10 or more, but, they're roughly the same order of magnitude. So if you were given a task, or if I give you a task to do a finite element analysis on this mouse, I would say go ahead and use like tetrahedrons, hexahedrons, and you'd be just fine, okay? But if you compare that to an object like, say, my phone right here, right? And so if you look at the height and the width of the phone, these are roughly the same, right? But if you look at the thickness of the phone, right, this dimension of the phone is way thinner than all of the other ones, right? And so this is something that I would characterize as a thin geometry. And for these ones, you might want to consider using different element types. Okay. All right. And so, kind of the opposite. And so, geometries that are characterized like my phone, I would call them either thin geometries or slender geometries. Okay. And the reason for that is, these shell and beam elements are, they're kind of naturally suited to the geometry that you're trying to model. Okay. And so, from here on, we'll define what shell elements look like, what beam elements look like, and what properties they have that make them really suitable to mesh, these certain kinds of geometries. Okay. Okay, any questions on this so far?
Oh, yeah, good question.
Mhm.
For those, when then it's slender geometries apply to thin inner diameter, like thin thicknesses compared to like inner diameter and outer diameter.
Yeah, no, it's a good question. So yeah, shells are actually a great way to do those kinds of so you're talking like maybe like a thin walled pipe where the inner diameter and outer diameter are very close. Yeah, that's a great candidate for a shell too. And actually, you know, there's I did a little bit of research on that when I was in grad school too, where you know I did simulations of blood vessels, and blood vessels are another type of pipe where the inner diameter and outer diameter are pretty close to each other. And so I was actually doing some research where I was trying to use shells to model how you know the blood vessels kind of breathe in response to blood pressure. So yeah, it's because it's used a lot. I knew it's used a lot in pipe flow, and so it makes a lot of natural sense to use it for blood vessels too. Yeah. Mhm. Okay. All right, so let's define what shell and beam elements look like, and let's kind of talk about the situations where they're used well. All right. And so shell elements, you know, think of like the shell of a snail, right? And so if you think of a shell of a snail as something that's really thin, and so visually, what shell elements look like, they look like basically thin sheets or thin surfaces, right? And so you know you can kind of almost think of them as like pieces of paper. Right? And so technically speaking, they're 2D elements. Okay. Okay. But they're not used in like a 2D context here. And so we're using 2D elements, but we're using them to model three-dimensional objects. Okay. And in particular, the types of 3D objects that we use them for are ones that are really thin. Okay. And by thin objects, what I mean by that is that one of the dimensions of your object is much less than the other ones. Okay. And so I think kind of the canonical example of this is that is like a thin sheet of metal, right? So let's say that you have a piece of sheet metal here. Okay? And let's say that's really thin. Okay. So maybe the thickness of the sheet metal might be like, you know, maybe a 1/4 inch, maybe 1/8 of an inch, right? But it's much more longer than it is wide. And so let's say that, you know, your length here is on the order of meters, and the width here maybe is also on the order of meters. Okay? And so what shell elements does is that instead of having this, you know, modeled as a 3-dimensional object, what we can do instead is model it as a 2-dimensional sheet. Okay. And then we can break up the sheet into 2D elements. Okay. Whereas if we broke up the sheet into 3D elements, right? Right, maybe it looks something like this. Okay. And so let's say that here we use 3D hexahedrons. Whereas here we use 2D quadrilaterals. Okay. And let's say that we use the same number of elements in both cases, right? And so let's imagine that the checker pattern is the same. Okay. You know, the one that's going to be cheaper here is actually going to be this one. Okay. because on a per node basis, and we saw this, last week when we were looking at the number of nodes and the number of functions, this is going to be cheaper here. Okay. And kind of the magic of shell and beam elements is that in addition to being cheaper, it's actually going to be more accurate too, believe it or not. Which is very, very strange in this class, because usually you don't get both of these at the same time, right? Because usually if you're talking finite elements and you want to go cheaper, that usually means you're going to sacrifice accuracy to some degree. And the other way around is where if you want a more accurate solution, you usually have to pay for that in terms of, more element refinement. Okay? But by using these specialized element types, you kind of get both at the same time. And so it's kind of a unique kind of it's a win-win situation. That's, that doesn't happen that often. And so when you can use shell elements and, and we'll talk about beams in a second, they're actually, a lot better. And after I introduce beams to you, then I'll kind of explain why this is, why you kind of get both at the same time. Okay, any questions on shell elements? Okay. All right, so let's talk about beams. So if shell elements are 2D elements used to model 3D objects, beams are going to be 1D elements. 1D elements that we're going to use to model 3D objects. Okay. And the class of 3D objects that we, or the types of 3D objects that we use beams for are slender geometries. Okay. And so what does slender mean? Slender basically means that it's you have one dimension or one length dimension in your object that's much greater than the other two. Okay. And so it looks like, a literal beam. And so if you think of like a structural beam for a structure, right? You have one dimension, which is the length of the beam, that's much greater than the height or the width of that beam, right? And so just right in front of me, you can see that, this stylus that I'm using, this would be a great candidate for a beam element because the length of the stylus, is like this much. But if you look at the cross section of the stylus, it's way smaller than that. Right? And so visually, you might have something like this, right? Maybe like a rod. And we're literally just going to replace this with a line. Okay. And again, maybe we mesh this rod, maybe we mesh it with hexahedrons again. Okay. Okay. Whereas for the line, we haven't talked about 1D elements yet. But basically, the only 1D element that's available to you is a line element. Right? Okay. You don't really have a lot of creative freedom in 1D. You can only there's no shapes in 1D. There's only one, which is a line, and so that's all that you have available. Okay. And the thing with 1D line elements is that they are extremely cheap. And so on a per element basis, you have very, very little nodes. And so, this is very, very cheap. Right? And so again, if you have slender parts of your geometry, then it'll pay a lot for you to do it with beams instead. Okay.
Dr. Tran, you were talking about a beam element that would span the entire length. of that kind of rod?
Yep. Mm-hmm. Oh, it would be broken up into several beam elements, and so
Okay.
yeah, and so you would basically have several different line segments that break up this rod, and that's something that you can control too. So you can control how fine you want to break this up. But instead of using 3D like hexahedral elements, you're instead using these 1D line elements instead.
So would that mean that it's cheaper because the relationship from each node to each node is more linear in fashion?
It's the fact that per element you have way less nodes that you're computing. Because remember, hexahedrons, think of the quadratic type. The quadratic hexahedrons, you have 20 nodes per element, and so for each of these blocks you have 20 nodes. But for a quadratic 1D line element, you only have 3 nodes per element. And so that's almost a drop in a whole order of magnitude. So you go from 20 to 3, that's going to be a lot cheaper for you to compute than 3D. Yeah. All right, question. So is the accuracy about the same for a 1D line element versus 3D hexes? And so it's for most cases, on a kind of on a per cost basis, the 1D line element is actually going to be more accurate. And we'll talk about that on the next page about why that is. Because when you have these kind of thin and slender geometries, you have a very interesting effect that happens where, it starts to get really difficult to compute stresses really accurately unless you refine to like a crazy amount. And so, I was planning not to really show this until the end if we have time, but one thing we talk about a lot in finite elements is convergence, right? And so you have this, this 2D graph right here, where on one axis you have the finite element result, okay? And so let's say the stress or something, right? And on the x-axis here you have the number of elements. Okay? In theory, it's possible to achieve the same accuracy with both 3D elements and shell and beam elements. It's just that for shell and beam elements, you get there so much faster than 3D ones, right? And so if we use, let's say, if we use 3D hex elements and we use quadratic element type, okay, it might your mesh convergence point might look something like this, okay? Where let's say that this once it flattens out, this is the converged value, and so you can see that we reach convergence maybe somewhere around here, okay, for a very high number of elements. But for shell and beam elements, the plot looks something like this. And so you achieve the same result. And so, the accuracy is the same. It's just that you get there so much more efficiently. And so you can get this accurate result with way less elements compared to the 3D one. And so in red right here, we have shells and beams. And in blue here, we have 3D solid elements. Right, and so for the cases where you can actually use shells and beams, you're gonna get a converged solution or an accurate solution for way less of the costs. Yeah, but I want you and kind of the reason I didn't want to show this too soon is that you can only use shell and beam elements for the specific geometry types, and so you want to make sure that you're using shell elements for thin geometries and you're using beam elements for slender ones. Otherwise, then it's then kind of all bets are off. Yeah. All right. Any questions on this? Yeah, no, an I-beam would work for this. And so if it's a really long I-beam, you can replace it with the beam element.
So cross-sectional shape won't affect it so long as the length.
We'll talk about the effect of cross-sectional shape because that is something that's really important for beams. So beam elements have a special way to kind of incorporate that cross-sectional shape. So yeah, that is something really important for beams. Yeah. Okay. Question. So is a horizontal line number of elements? Shouldn't it be number of nodes? It's both. I mean, it's they're kind of this graph can kind of work for both. And so you'll achieve a much more converged solution for both number of elements and the number of nodes. Yes. Mm-hmm. Okay. All right, so let's talk a bit about why shell and beam elements are better in these circumstances. All right. And so when you mesh a thin or slender geometry with a solid element, one thing that you'll probably see often is that you'll get this behavior that I like to call just one element through thickness. And so let me draw kind of a thin sheet, just like we did before. Okay. And so by one element through the thickness, what I mean is that if you put let's say a hexahedral mesh on this plate, your hexahedral mesh is likely going to look something like this, unless you refine it to some kind of crazy amount. Right? Okay. Then your mesh is going to look something like this, right? Okay. And so if you look at the mesh density in, let's say, this direction right here, okay, then you can say that we have pretty good mesh density in this direction, because if you count the number of elements going across that dimension, let's say that we have 1, 2, 3, 4, 5, right? And so we have 5 elements in this direction. Okay. Let's count the elements in this direction right here. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so that's pretty good. So even in this really simplified example, we're getting good mesh density. Okay. But if you count the number of elements in this direction, in this height direction, we only have 1. Okay. Right. And this is a situation that you actually want to avoid most of the time. Okay. Okay. Right. And so if you're using solid element types, usually you want to have several elements, at the very least 2. 2 is significantly better than 1, but 3 is also much better than 2, and 4 is better than 3, and so on and so forth. But 1 is usually pretty bad. Okay. And the reason you want to avoid doing this, a lot of it has to do with the fact that if you look at this node right, or this element right here, okay, and we look at all the nodes on this element, okay, all of the nodes here are actually on a boundary. Good question in the chat. Let's see. Yeah, actually, yeah. So that's a great example. So for the last activity that we did, we did a signpost analysis, right? And so actually in that one, you have kind of a prime example for both a shell and a beam. And so for the sign, the rectangular sign, that's a fairly thin geometry. And so you could reasonably actually use that, do that with a shell. And then for the post itself, the post is fairly slender. And so it's much more long than it is kind of, in that case, we had a cylindrical post. And so, the diameter of that post was much less than the length. And so, and I thought about that too. So, but I wanted to focus on other things in that example. But you can definitely do that activity with shells and beams. And you would actually get, a much more, you'd achieve an accurate solution with much less elements than what you did for that activity. Yeah. All right. And so when you only have one element through the thickness like this, you're going to have a bunch of nodes in the same element, all of it on the boundary, right? Or another way to say this is that you're not going to have any interior nodes. And that can be kind of dangerous because what can happen is that when you're just solving for the deformations, right? You could have a situation where you have a boundary condition applied on the top right here, okay, and then you can have a different boundary condition applied on the bottom, right? And so you're going to have one element that's kind of sandwiched between these two boundary conditions, right? And there's going to be really no way for the solution to kind of reconcile anything in the middle, okay? Right. And so if you have a certain type of boundary condition on top and a certain one on the bottom, you're going to have this one element that's kind of sandwiched between them. And actually all the elements here would be exposed to that, and that's usually not good. Okay. But the other kind of important reason where having all your nodes on the boundary can be bad is when you're going in and you're going to compute things like stresses. Okay. Because remember, stresses, when you compute stresses in your finite element simulation, it relies a lot, or it relies completely on computing derivatives of your deformation field. Right? And so if you have a situation where none of the nodes on your element face on interior, the derivative calculations can be they have a big potential to be really inaccurate. Okay? Okay. Because again, you're basically computing the derivatives between two boundary points, right? And even if you don't explicitly apply a boundary condition on one face or the other one, there still is some boundary effects that occur, at those boundaries, right? Because remember, if you don't apply a boundary condition on a certain face, then ANSYS will apply a no stress or stress-free boundary condition. Okay. And so if you have kind of two, if we consider a situation where we have a stress-free boundary condition on the top and bottom, if you try to compute the derivative, between those two things, you're going to end up with something that's pretty inaccurate, or at least has the potential to be pretty inaccurate most of the time. Okay. And so, you know, for most situations or for most structural finite elements, you want to avoid situations where you only have one element of the thickness. Okay. And so if you come across these types of geometries in your CAD model, you really only have kind of two options available to you. So one thing that you can do is you can just refine the shit out of this geometry and just make the elements, you know, like minuscule, as small as possible, right? And so if you refine this like crazy, and so let's say that you have an element that looks like this, right? And so that solves the issue because now you have multiple elements through that thin surface, right? And you can get an accurate solution from this, and that's, you know, there's nothing wrong with that. Or you know, but where you're going to pay for this is you're going to wait, you know, eons for your solution because you're going to have, you know, millions of elements in your mesh, and that's not, you know, a lot of times that's not practical. Okay. And so the other option that you have is to instead of using solid elements for these situations is to use your shells and beams. Okay. And shells and beams have a kind of one unique advantage in their mathematical formulation that make it so that they can compute stresses a lot more efficiently without having to, you know, refine the shit out of something like this. Okay. Any questions on this so far? Okay. All right. And so let's talk about how do shells and beams handle this situation. Okay. And in particular, I want to focus on stress computations and derivative computations. And so shell and beam elements, they, you know, and they're kind of both, you know, two peas in the same pod. And so, you know, they have kind of a very special mathematical formulation of their elements. And so we're not going to get into the nitty-gritty details of what they are. But basically what you can think of is that, you know, you can think of it as that they explicitly solve for these derivatives as part of their formulation. Okay. Because normally for a solid element type, like so for your tetrahedrons or hexahedrons, they only solve for the deformations, right? And so they solve for the X, Y, Z deformations in that you know, for that element. Okay. And so shells and beams will compute this deformations. Okay. And so your shells and beam elements will compute the deformations for you. Okay. But in addition to this, they can also compute rotations. Okay. Okay. And the rotations, that also has three components. And so it's also X, Y, Z. Okay. All right, so what does this mean? And so if we take a typical, you know, I'll do this in 1D just because it's a little bit simpler to do. Okay. And so let's say we have a typical beam, you know, maybe it's deflecting up like this. Okay. And so at this node right here, okay, normally what we're solving for in a solid element is just, you know, how much is deforming. Okay. And so basically just the raw computation of, you know, after we apply the loads, how far is this node kind of traveling away from its initial location? Okay. Another thing that we're also computing are the rotations, right? And so we typically denote those as angles. Okay. And what the angles tell you is that not only how far this node is deforming, but it also give you the slope of the beam, as it approaches that node. Okay. Okay. Right. And so I drew an example here with the beam, but the shells are exactly the same way too. And so for the shells, you're also going to be computing those rotations. Okay. And these rotations are literally baked into the beam equations and baked into the shell equations. Okay. And so it's something that that the finite elements is it's actually looking for. And so since these rotations are baked right into the equations, then we can compute them with much higher certainty. Because if you think back to our solid elements, right? When we compute our stresses, and we compute our strains, those are what are called derived quantities. And so those are computed after we do the deformations, right? And so its accuracy is going to be naturally less because we're basically computing the deformations first. And then we're approximating the stresses and the strains based off that deformation. Okay. Whereas for the shell and the beam elements, you can almost think of it as like we're solving for stress and strain almost directly. Okay. And so even though the elements are a lot thinner, we actually end up with a much more accurate, or I would say we arrive at a converged and accurate stress computation a lot more easily than our solid elements. Okay. All right. And so if you compare these two options, and so if you compare using a shell and beam element to meshing the shit out of a thin geometry, then using shells and beams are usually going to be the superior option. Okay. At least in terms of stress computation. All right. Any questions on this? Okay. All right. So let me talk a little bit. Before we go into talking about how we actually form shells and beams, let me talk about when you can actually use them. Okay.
Excuse me, Dr. Tran.
Yep. What's up?
Are you going to talk about like how is it possible to just get stress and strains directly? I mean, not approximately from the shells and beams.
I wasn't planning to, just because we'd have to kind of do a deep dive into the differential equations for shells and beams. We'll actually see a little bit of it, because we are going to cover beam elements when we do finite element theory. I think we're doing that in maybe 2.5 weeks. And so we'll see a little bit of that, but kind of doing a deep dive, I think would kind of take us down a different path that I don't really want to go to. But
Got it.
But I can show you some readings that if you're interested, where I can show you where you do that. Yeah.
Yeah, it just like came to my mind, like how is it possible to just, not approximately getting it?
Yeah. It's
Thanks.
mostly due to how the derivatives are calculated in solid elements. But yeah, we can talk offline, and I can give you some reading on how that's done. Yeah. Okay. All right. And so up to this point, we've been talking about how you should use shell elements for thin geometries. You should use beam elements for slender ones, right? But these are kind of very I would say qualitative terms. And so, it'd be a lot more useful to say that, if our dimensions are this, then we can use shells and beams. Okay. And so, unfortunately, there's no hard number. And so there's no hard rule about when you should use shells and beams. Okay. Right. And so there's no hard number for it, and because if there were, then ANSYS would just do it automatically for you. But it's a lot of it is kind of application specific, and it's a lot of it is kind of user preference too. Okay. And so I'll tell you right now that there's if you ask two different finite element engineers, they'll probably give you two different answers for what is kind of the threshold for when you should use shells and beams. Because a lot of it depends on the kind of work that you do. But I'll give you my rule of thumb. But I'll tell you that I know colleagues that'll disagree with me on this. And it's not a vehement disagreement. It's not like we get into arguments about this. It's just that everyone just kind of has their own personal preferences. Okay. And so the rule that I personally use, and of course you guys are free to use it too, is I use a 10% rule. Okay. And what I mean by that is if your thin or slender dimension is less than or equal to 10% of the other ones, then that's the threshold where I say that this is really thin or this is really slender. Okay. Right, so I take a very relative approach to it, and so I do it kind of based on the relative dimensions of the object compared to the other ones. But I know certain people that just use a hard number, and so they said that if a dimension here is less than a quarter inch or less than an eighth of an inch, then they're going to use shells for that. Okay, and so it doesn't really matter what the other parts of the geometry are doing, and so that's kind of another school of thought for this. But I do it just kind of based off relative dimensions. Okay? And so if you draw kind of a thin sheet like this, and so if we say that this dimension here is the length, and this dimension here is the width, okay, and this small dimension is the height, right? And so in order for me to consider this a thin enough for a shell, then the height dimension has to be less than or equal to 0.1 times the length, okay? And the height has to be less than or equal to 0.1 times the width. Approximately. And so these aren't hard numbers. And so, practically speaking, most of the times I'm mostly just going to look at a geometry and see if it's going to be thin enough or slender enough. But if I were to measure it, then this would be kind of the measurements that I would use. Okay. And so another example, I think going off a question someone else asked earlier. And so, you know, another good place where you can use shells is for like a thin walled pipe. And so the threshold I used for that one was that if the difference between the outer diameter and the inner diameter, if that was less than or equal to 10% of the inner diameter, then that's when I would start to consider using shells. Right? Otherwise, I would use cell elements for that. All right. Any questions on this before we go into how to actually make these in practice?
So these shells or beams don't necessarily have to be like extremely small items, like an airbrush gun's needle that's extremely small versus it could just be like a geometry or a shape or whatever, like a glass window that just has a very thin width.
Oh yeah. And so like a window would be a great candidate for a shell. And so yeah, it doesn't have to be anything extreme. And so I think for a needle, you're probably talking on orders of like, you know, 1,000 to 1 for like kind of the aspect ratio for that. It doesn't have to be that extreme. And so usually for me, I use 10%. And it served me pretty well. And so it doesn't have to be that big. And so like if you consider like your phone, right? You know, I'll try not to drop my phone again. And so, you know, if you look at the thickness of your phone, you know, this is probably around maybe 10% of this width. You know, if I had to kind of guess it. And so, you know, if I were to do a finite element analysis on this phone, then I would use a shell for it just because it's you know, just because it is a lot thinner than it is wide or long. Yeah. Okay. All right. So let's talk about how do we actually make these in practice. And so, you know, I want to talk about it a little bit today, and then on Thursday we're actually going to put this in practice through the activity. All right. All right. So first thing I want to talk about is, you know, one other thing that makes shell elements unique, and I should have mentioned this before, but one aspect of shell elements is that we're kind of taking a 3D geometry and kind of flattening it, right? And so you can almost think of it as we're kind of losing that thickness information, right? Okay. And so I think a fair question to ask is, you know, even though that dimension is really thin, you know, that dimension is still, that thickness dimension is still going to be important to us. And so, you know, the question to ask is, you know, are we losing that thickness information by flattening the shell? Okay. Right. And so thankfully, you know, the answer is no. And so we still have that thickness information. It just takes a different form, right? And so instead of geometrically actually seeing the thickness in your in the 3D part, that thickness now just becomes a material property. And so just like, you know, we enter a number in for things like the Young's modulus and things like the Poisson's ratio, you know, for shell elements, you know, we have to also enter information, you know, what's the thickness of this shell, right? And so actually, you know, you all have already seen an example of this in action, right? And so if you think back to our signpost activity, you know, think about the wind application surface on the left, right? So that phantom surface that we had. if you remember, one of the things that we did in the last activity was that we assigned a thickness of 1e minus 3 to this piece of tape, essentially. Okay. And so in actuality, that thin, piece of tape surface there was actually a shell. And so it was a shell that was made in the ANSYS CAD software, right? And before we can actually start using it, then we had to assign a thickness, and that thickness was just a number. Okay. And so for other shells, it's the same thing. And so you have to basically apply the thickness as a, basically like a material property. Okay. All right. And so with that in mind, let's talk about the 4 methods to basically how to create a shell element in practice. Right? And so there's 4 elements here, but in practice, you only really use one of them. And so that one is kind of the most practical. It's the one we're going to use Thursday too. Okay, so let's go over kind of the first 2. All right, so the first way that you can create a shell element in ANSYS or any finite element software is to just draw it from scratch, right? And so method 1 is to create a 2D sketch. Okay. And so if you just draw a sketch in 2D, then what you can do is you can just, assign it to be a shell surface. Okay. So pretty straightforward. And so you can basically just draw a sketch and then make it into a shell. And so if you think back to our ANSYS activity 1, we didn't quite do this because that was kind of a fully 2D simulation. But it's the same idea, right? And so you basically draw a sketch, and then you basically say that, I want the sketch to be a shell surface. And then ANSYS will say, your wish is my command, and then it'll create your shell for you. All right, method 2. So method 2 is basically what you can do is you can extrude. You can extrude an open sketch. Okay. And so by open sketch, what I mean is basically a curve that doesn't meet on itself. Right? Or actually, this can work for any sketch as well, but it can especially work for open sketches too. Right? And so let's say that we draw kind of a sketch that maybe looks like this. Okay. And so it looks like a speed bump or something. Okay. You can extrude this into the page, and so you end up with a surface that looks like this. Okay. And so that extruded line then becomes a thin shell surface. Okay. And so methods 1 and 2, I would say are probably among the cleanest methods for you to develop a shell element. But you kind of need to plan ahead to use 1 and 2. And so if you want to use 1 and 2, that kind of implies that you're making your CAD geometry, from the ground up with the intention of using shells and beams. And so if you have the kind of foresight, or probably more rarely, if you're in control of the CAD model that gets produced, then you can use methods 1 and 2. But what can happen a lot of times in companies is that, as the stress analysis or as the finite element engineer, you don't really have control over the CAD model. Some other engineer might produce it, or maybe you're producing it, but you have to use it for other purposes, like for rendering and for showing off the part and for design and machining purposes. Okay, and so for those cases, you're probably not going to use these first 2 methods because you're making your CAD with other intentions in mind. Okay, and so method 3 is probably the most common way that you can use to create shells. Okay, so any questions on this so far?
Yeah, so then for like a cylinder, or for example, like that thin wall pipe, would that essentially just be like a square almost, with like fillets on the side?
Yeah, so I mean, for a pipe, that's why I said, you can do this for a non-open sketch too. So for a pipe, you can draw a circle. And so you can extrude this too, but you have to be careful that you don't use the regular extrude. So if you use like kind of a regular solid extrude, you're just gonna get a solid pipe. And so you have to use, I think it's called like line extrude or shell extrude or something like that, in order to get a thin wall pipe from this. And so, you can do this with closed sketches too. You just have to be careful about the extrude function that you use. Yeah. All right. And so let's go over method 3. We are running a little bit short on time, and so I want to make sure I get to the beams too. Okay. All right, and so method 3 is called a mid-surface operation. And so for a mid-surface operation, what you're doing essentially is that, you're going to look at a 3-dimensional part, okay? That may be really thin. Okay. And so let's say that you have a CAD model, and this is one region in your CAD model where you can say that this is a fairly thin geometry. Okay. For a mid-surface operation, what you're going to do is that you're going to select two parallel faces. Right, and ideally, these two parallel faces should be pretty close to each other. Okay. If they aren't close to each other, then your geometry probably isn't thin at all. Okay, and so for this surface here, let's say that we have this surface in red. And then we have the adjacent surface in the background of this thing that I can't draw because I can only draw things in isometric view. And so what's going to happen is that when you select these two parallel faces, then you're going to basically create a shell that is placed right in the middle of these. Okay. Hence the name mid-surface. And so you basically create a shell surface right in the middle of these two. Okay. And so what you end up with is something that looks like this. And so in the middle of those two, you're going to create a shell. Okay. Remember, it's a 2D sheet. Okay. Okay. And then around that is the 3-dimensional object that kind of used to be there. Okay. Okay. And so this method works for for an existing CAD model. And so that's why this is pretty popular, because it's someone else is going to create your CAD model, and if you see two surfaces that that are pretty close, you can then just create a mid surface that goes right in between. Okay. All right. Any questions on this? So this is what we're going to do on Thursday. And so on Thursday, for the thin parts of our geometry, we're going to use a mid-surface operation to create a shell in the middle of it. All right. Okay, so there is a fourth method to create shells, but I am going to skip it just in the interest of time because I do want to talk about beams. But the fourth method for creating shells is actually not that commonly used to. So it has, I would say, very niche uses, but I've only really used it as just kind of a fun thing. But and so I wouldn't worry about it too much. But if you are interested, we can talk about it on Thursday. But I personally have never used it for anything practical. And so let's talk about beams because I want to make sure we get through that today. All right. And so remember, beam elements are 1D elements. And so by creating these 1D elements, remember we're going from a, basically a 3-dimensional object down to a 1D one. We're losing not just one, but we're losing 2 dimensions worth of information. Okay. And so remember, for the shell elements, we had to keep track of the thickness of our shell, and so that was just a scalar parameter. And so for a beam element, we're taking basically 2 dimensions, and so we can no longer just store just a single number. Okay? And so what we need to store instead is cross-sectional shape information. Right, and so because if you looked at several cylinder objects that are used in engineering, there's lots of different cross sections that are used, right? And so you have a basic a cylindrical cross section, which is just a circle. Okay. Okay. You can have the famous I beam. Okay. And you can have L beams too. Okay. I spelled oil unintentionally, but I guess it's there. It doesn't mean anything. It just happened to be OIL. And so, as you all probably know, the cross-sectional shape of the beam, has an influence on its solution. One major way that the cross-sectional shape makes a difference is in the computation of the moment of inertia. Okay. And so if you think back to your, and we talked about beam theory, earlier in this class too, right? In order to compute our beam theory solutions, we had to know the moment of inertia. Okay. But since these beams are going to be loaded in kind of an arbitrary way in 3D, you need to know the moment of inertia in kind of all different directions. Okay. And so, the way that this is usually handled in a finite element software is that whenever you make a beam, you also have to kind of draw out what the 2D cross section looks like. Okay. Because ANSYS, any finite element software needs to know that in order for you to compute the solutions, and in order just to solve the beam equations, you need to know what that cross section looks like. Okay? And so if you're creating your beam from scratch, and we'll go over kind of two methods for creating beams in practice. If you're creating your beam from scratch, then you actually have to open up a new window where you actually have to sketch out what the cross section looks like with all the dimensions, listed in there. Okay. All right. Any questions on this? Okay. All right. So quickly, let's go over kind of the two main ways to create beams. Okay. And they kind of have similar applications as the two ways that we compute, or the several ways we create shells too. Okay. All right. And so we have one method that can be very clean, but you also have to plan ahead for it. And so method one is to basically define a line or sketch a line. Okay. And so you would sketch this line in your CAD software. And so you can do this in ANSYS, or you can do this in SolidWorks. Okay. And then once you've drawn your line, then you basically assign it as a beam. Okay. Right? And so visually, it might look something like this. Okay? And so let's say that you draw a line in 3D space. It doesn't even have to be a straight line, and so it can be a curved line as well. Okay. And so in this situation, once you assign it as a beam, ANSYS will say that, okay, you've made this beam here. Now you have to draw for me what the cross section looks like. Okay. And so, maybe you're drawing a kind of a backward C beam like this. Okay. Right. And so you have to kind of draw what that cross section, is looking like if you assign the beam from scratch. And there's a lot of pre-made or pre-made beam cross section templates that you can start from. Okay. And so that's pretty convenient. And so it's not like you're drawing each of these lines from scratch. Usually you're starting from a template, and then you're just kind of setting what all these dimensions are. All right, and so that's method one. And so method one works great if you can plan ahead, if you have control over the CAD. But again, most of the time you don't do that. Okay. And so most of the time, you're going to be given a CAD model, and you have kind of you notice that there's slender geometries in the CAD model. And so what you can do is you can extract, beams from certain parts. Okay. And this is what we're going to be doing on Thursday. And so let's say that, you have a thin, square beam like this. Okay. And this part's actually pretty easy, because all you have to do is that, if you open up the extract tool within your CAD software, and you just point and click at a place where you want it to be a slender geometry. Most of the time it's pretty smart, and it'll say, okay, I see that you've clicked on this geometry right here. Let me go ahead and create a beam element for you. And so it's pretty nice, actually. And so you can just kind of click, and then it'll just turn certain parts of the geometry into a beam. Okay. And the nice thing about the extraction method is that it'll automatically read what the cross section looks like. Okay. Okay. And so you don't have to assign it yourself. Okay. And so it'll pick it up kind of straight from the CAD model. And so it's really just a point and click, and then you're done. All right, any questions on creating beams in FEM? Okay. All right, so we're just about out of time, and so, but I did want to say one thing before we leave today, because everything that we went over today with shells and beams it all seems great, right? It seems like shells and beams, we should use them all the time. And so the thing that I didn't really tell you about shells and beams is that when you actually create them in practice, sometimes it can be really annoying to deal with the CAD. And so you'll see this on Thursday that it's not all sunshine and rainbows with shells and beams. And so often what happens is that when you start to do mid-surface operations and once you start to do beam extractions like this, then your geometry might not connect to each other like it used to. And so some parts that should be connected to each other, all of a sudden they're not going to be connected. And so you're gonna need to do a lot of cleanup on the geometry in order to get it back to a state where you can actually run a finite elements. And so there is some work involved. And so if you can use shells and beams, they work great. But sometimes they can be a little bit annoying to work with as well. Okay, but we'll get to know that on Thursday, right? Okay, and so I know I went over time a little bit, and so I apologize for that. So thank you everyone for coming today. I'll stick around if you have any more questions on the lecture. But if not, I'll see you on Thursday for our next ANSYS activity.
Thanks, Dr. Tran.
Yep. Yep.
I'm just kind of like I can't seem to picture in my head what you meant for like cylinders or like thin wall pipes.
Yeah. Mhm.
Do you mind drawing like some sort of like picture for me?
Yeah.
Like, do you literally mean like a shell around the geometry?
It's a shell that would replace the thin wall of your pipe. And so let's say that you have a pipe that looks like this. Right? And then you have fluid that's going through it, right? And so let's say that this is filled with fluid. Okay. And so this this black part here, this is our pipe, right? And so this is like our iron pipe or something. Okay. And so when I say that we can replace this with a shell, instead of having a pipe that has actual thickness like this, we have just kind of a line that kind of goes around that that space. And so you can almost think of it as we're kind of getting rid of the outer diameter and we're just assuming that we're flowing with the inner one. Or you can kind of think of it as maybe we created a mid surface where in between the outer diameter and the inner diameter, then we created kind of a thin circular line, and then that's going to be the new wall of pipe. But instead of having thickness, now we say that the thickness here is some variable. Right, and so we're storing that variable now as a number instead of being geometrically represented. And so just like on the left, you would have water that's kind of flowing through the middle of the pipe, just like that.
And so this is kind of like ignoring the length of the pipe.
You still have the length of the pipe, and so the pipe still goes into the screen, like this. Right, and so for the shell, it goes into the screen just like that as well. It's just that it's just the thickness of the pipe is now being replaced by a thin shell. Yeah. Yeah, I think when we do the activity on Thursday, I think it'll be once you see a mid surface in action, then it kind of becomes clear about what happens. So yeah.
It's literally like a fancy surface.
Exactly. Yes. And so we're replacing kind of something with actual thickness with a phantom surface. Okay.
Thank you.
Yeah. Mm-hmm. Yeah. I think once you see it in action on Thursday, it'll be a bit more clear because you'll actually click on the two surfaces, and you'll see it be replaced by a shell kind of in kind of live in front. And so with the with a whiteboard like this and with drawings, it's a little bit hard to visualize, but once you see it, then I think it becomes a lot more clear. Yeah.
It's almost kind of like a wrap, like a wrap with an object in a way.
Yeah. Yeah. You can think of it like that too. Like you're you can almost think of it as like you're kind of wrapping something around with like plastic wrap, and then you're taking out, whatever was there, whatever wall that was there before. Yep. Mhm. Yep.
I was maybe I'm getting too into it, but I was looking at the bearing connection.
Yeah.
Option in Ansys. And like I was reading a form or whatever, and they're saying that if you're doing a static analysis, that won't work
Mm.
because it assumes that you have rotational motion there.
Yeah.
So I was going to try that because literally it is a bearing, but
Yeah.
I'm going to try to stay away from something that isn't a static structural analysis.
Yeah,
Just to not destroy myself.
Yeah, I would stick to just bonded and no separation. Those should work fine for a static simulation.
Okay.
Yeah, for the I have heard of the bearing concept, but I think that's more for dynamic simulations where you
Right.
actually have, because we are doing a static one, and so even though we don't want that much friction, it's not actually going to be spinning it.
Correct.
And so for the bearing thing, I think that's for modeling like engines where the shaft is spinning at
Right.
like 1400 RPM. And you
you're
actually
looking
wanna-
for some
you actually
kind of
wanna
heat
model.
distribution there or
Exactly,
something.
exactly.
Okay.
Yeah.
Yeah. Cutting it didn't end up being bad when I decided I was like, wait, I can just delete the other housing.
Okay,
The other
nice.
bearing.
Uh-huh.
So then all I had was a shaft left, and I
Nice.
just put a midplane there,
Okay,
and I just cut it.
perfect. Yeah, I read
So I'm like, I
that.
don't need these. I can just delete them, right?
Yeah. No, that's yeah, I think that's
Yeah, that
that's
made it
perfect.
easier opposed to adding the whole symmetric boundary condition thing.
Right.
But yeah, Dr. Weiss apparently just fast forward our midterm 2 weeks, so that
Uh-huh.
kind of just throws everything that I'm doing in the jumble because I got to be prepared for it by a week from today.
Oh yeah, Jacob told me that she was
I was like, what?
either giving you next week or like 2 weeks from that, because she's already set which days that you guys come to campus. Right?
Yeah, exactly.
Actually, let me close this so we can.
Generally,